Recording in progress. All right. We've begun. So we're going to go over both exam 2 from the fall and the one from the spring that is in respondus form real quickly. So first things first, do you get how to do number 1?
Yeah, this one he actually on the solutions, it says 1 gigabyte, but he changed it to 10 gigabyte.
Yeah, which is weird.
But I
But
mean,
even in 1 gigabyte, the math for this is rather simple if I annotate. It's literally as simple as taking however many gigabytes you have, which in this case in 1 gigabyte is 1 times 10 to the 9th bytes. So we'll just denote that with capital B here, and then simply divide it by the amount of numbers you have here, right? So let's say basically, because the 32-bit, the TCP sequence number, one TCP sequence number is equivalent to 1 byte of your data. So basically he's asking is how many gigabytes, right, can you represent with a 32-bit TCP sequence number without any wraparounds, or how many wraparounds will you get? So if you do this, you'll do this divided by what's 2 to the 32. I don't care. I'm just going to say 2 to the 32 because I don't have my calculator on hand. It's just that simple, because your outcome here should be unitless. So this is in bits. So honestly, no, but it's 1-to-1 here. It's 1-to-1 because one of these is meant to represent a byte anyways. So you do that, and this ends up being approximately 2.3 if you use a calculator. But since it's asking how many wraparounds there are, there's only going to be 2 wraparounds. So if you wanted to transmit that 1 gigabyte without any wraparounds, your TCP sequence number would need to be larger than 32 bits. And this similar type of math can be used to figure out how long wraparounds will happen. You just need to know, instead of how much data you're transmitting, you need to know the bandwidth of the network, and that'll allow you to calculate that the other way around to get how long it'll take for a single wraparound to occur. But that's just some algebra. So just keep your units straight and you'll be pretty good with those for the benefit of the people at home. So now we'll scroll down here. I'll pull up another annotate again. So this is the famed land bridge. So he says here that B1 is the root. So we will circle our root. So basically the goal with these land bridges here is to make sure you don't have any loops and you don't have redundant bridges. So you start at your node, your root, right? And then you check what are the adjacent ones to that. Adjacent ones are B7 and B3. All right. Is there any way that ascending something from B1 to B7 or B1 to B3 can cause a loop at the moment? No. That means you can add these. So these are both perfectly fine to leave. No problems here. Now you go and check what's adjacent to these next ones. B7 is adjacent. It's only adjacent to B2. So it does that. So as of now, then B3 is also adjacent to B2. So here's a problem. This is a redundant loop. So you get to choose which one of these you'd like to break, B3 to B2 or B7 to B2. But you have to take into consideration, if you cut, what is it? No, yeah, actually, now that I think about it, you can cut either of these, right? Do you see any problem with cutting something different? I don't think there's a problem. I think you can pick, because there's 2 ways to get to it.
I think if you cut D3, then D would have to be longer, because then a D would have to go through multiple bridges.
Yeah, would have to, yeah, sure. If you want to be efficient, then you cut the top link. So we put an X here for the top link. So there's that. And B3 we still have to consider. So B3 is adjacent to B2. We just considered that. It's also adjacent to B4, B6, and B5. So first things first, we look at this. Any loops formed by checking to B3? Nope, you're fine to go that way. So you can add that. Any loops formed by going to B6? At the moment, no, except now once you get to those 2, you'll notice that there's a loop node here. These are connected for no reason. So you can choose to terminate a connection. In this case, terminating B6's connection to I is fine. You need B6 to connect to J, so it is not redundant. And you need B3 to connect to H, so you're fine. Now over here, we can connect using B3, we can connect to F. So there's no reason to have B5 connecting to F. We can connect to F with B3. But if we go from B2, we can connect to B. So it actually turns out that B5 in its entirety is pointless. So the solution to this, since he says you may just mark them on the graph, is cut this link, cut this link, cut this link, and then down here is cut this link. And this simplifies the network because this is an unnecessary connection. These are completely unnecessary, so B5 in its entirety can disappear, but cutting it out on both sides is fine. And this down here is a loop from B3, B4, B6. That's unnecessary, so get rid of that. And that's what that solution looks like. Easy peasy. Mouse it. So now we go down to here, we do some IP stuff. Bonk, bonk, bonk. Annotate. Bonk, there we go. So we have Alice decides to start a small company. She asks her ISP, Go Chargers, to give her enough addresses for 1,000 hosts. Go Chargers has the following available address range for Alice. And there's the range. You have 5 different IPs. And then it says, in order to save money, what should Alice claim under CIDR to get the fewest or get fewest number of addresses possible to exactly cover her host? So she has 1,000 hosts. And he tells you to use your address and prefix form shown like this, and show steps to get full credit. So in here, you'll notice that there's a major commonality. So starting off, all of the available addresses have 192.1. So you can immediately start off, your answer will have 192.1 in it in all spots. And now there's just 2 more ranges to go. So you need to fill 1,000 addresses here. So you should be able to just do you know how he does this one specifically?
Yeah, he does. He does 4 times 255, and that tells you how many addresses are within that, which is 1,020.
So
you'll-
he overcounts. So that means he
Yep.
goes 19.1.0.0 as your low range, which would be this one at the top. And your
Yeah.
upper range would be, because you're actually just doing hex counting at the end of the day, or binary counting, whatever you prefer. 192.1, the front start, the same, and then this, and then this. So here you have 3. So that's 3 of the 4 times 255 addresses that can be represented on the end. So in reality, 4 times 255 is going to be what, 120? Or yeah, 1,020.
Yeah.
Yeah, 1,020. So 3 times 255 brings us up to what, 765? Yeah. So that brings us up to 755. So this is the 255, like the override, because these last 3 digits can reach 255. So every time you want to sub past 255, the next stage increments up to 3 or up 1. So we've done it 3 times so far. This number gives us access to 765 addresses. So now over here, we literally just do 1,000 minus 765, which should yield us 5 gives us 70, so 35, so 235. Technically. But the thing that he does is he puts in 231. But I'm pretty sure this isn't in decimal, is it?
I don't think so.
Yeah, I'm pretty sure that's why. So you'd have to convert that, and then this is in hex probably or something. Let's see. I'm gonna pull up a quick hex calculator. No. So I'm not sure why he does 231 here. So these are probably in decimal then, since this is up to 255. So this is 255 times 3. Or is it actually, or are these actually 256, you think? Because this would be, you can get to 255 here. So this field, a 1 here represents a 236.
Yeah, that might be.
So let's think about it that way. Well, 236, that just means this goes up 3 to 278. So add these together, you get 999.99, and then the 0 is excluded from this upper range. So that's 1,000. So that's what he did. This doesn't count as this. So in reality, what we should have is 768 yielding 231 or 232 on the output, but you also have to remember to subtract that you're actually working with 999 minus 768, which equivalent to 231 here, because the base case of 0 is already considered, and this would be your first case. So that's a +1 on that end. So then your final answer is going to be 192.1.0 dash, he says 22. So you remember why there's a 22 here?
Yeah, so like the 192 is 8 bits, the
Yeah.
1 is an 8-bit, and then you find the difference between the third octet, I think it's called.
Yeah, I get you now. So you go 22 bits in.
Yeah, because they don't change, like the third one is 0, so the binary is all 0, and then for
Yeah, so you go in here
yeah,
and
0 and 0, so the last 2 bits are the difference, so you just find
this, yeah, this number is somehow equivalent to 8 bits, this field. That the 0 is equivalent to 8 bits. So you have 0, 0, 0, 0, 0, 0, 0, 0. And then 6 will be the same here. And this 3, well, 3 in binary is just 1, 1. So this last 2 change from here to here to produce this field. So 22 of the bits are the same, as you mentioned. So that's how this works. There you go. So that's how that works. So that's just where he gets some of his numbers. His solution's a little sparse, a little sparse with the numbers. So it helps to see a better explanation. Scroll down. All right, IP subnet. If you want to create an IP subnet for IP addresses 192.11.64.0 all the way up to 192.11.127.255, what is the IP subnet mask that you must pick? So you go through octets. So the third octet over here. So I guess that what that means is each of these ranges is called an octet then. So the third octet, which is 64 for the lower range, is 64. So it's 8 bits. So 64 in binary is 0, 1, followed by, the rest of the zeros to get to 8. So there's that. Go to the third octet on this one, which is 127, which is instead 0, 1, but then populated with all ones. 2, 3 ones. All right. So the commonality between these two is the first 2 digits of the octet are the same. And then the remaining 6 digits obviously vary greatly from the top to top. Therefore, your octet mask should just be, do you add them together or do you? No, it's like a,
watch these lectures, the ones that match, you make those two 1, and then the rest of them become 0. The ones that don't match.
Yep, and there it is. So it's exclusive. So it's an inverse exclusive OR operation.
Yeah, kind of. I looked that one up, but
yeah,
in his lecture he just said
yeah.
make the ones that match. So
Yeah.
I'm just gonna go with that one.
Well, so exclusive OR would be the ones that are different get a 1, and the ones that are not. So I guess this is an XNOR then, an exclusive NOR. So you perform an exclusive NOR operation on this. So in doing so, that means that the third octet mask is going to be 1, 1, because these two are the same, therefore they're all ones. And then all of this goes to 0. So 1, 2, 3, 4, 5, 6. So this is your third octet subnet mask. Now, as we know, because we just said the rule is if the bits are the same, it all goes to 1. What happens to the total chunk that led before this? The 192.11, well, they're all the same. Therefore, everything there turns to a 1. Hence, the answer that follows looks like this. You have 255 for the first and second octet. Your third octet is this in decimal. Save you the work. This in decimal happens to be 192. And then we know that 0 and 255 is the other variable range, which means since these will all be different from the top to bottom, this range is a 0. So this is your subnet mask for this range of addresses right here. That's that. Bonk. Easy peasy. Scroll on down. There we go. Use a timing diagram to explain how the connection session is established between a server and a client over the internet using TCP. You must mark the sequence number that is used for each exchanged message. All right. So you start off with your basic bars. Use a note, one side S for sender, the other side R for receiver. Now for this one, this is like the sync packaging, that little handshake that they do at the start. So this is that what's it called? You just kind of got to memorize this. I think he explicitly
notes.
Yeah, he explicitly mentioned in class that he had a student come to him and tell him that they asked him this at a job interview. This like literally this question, like B right here, that this question was a job interview question. So first things first, we send our start. So what was sent in this message? Well, you're using the sync packet, right? Using the sync message. So the notation for this is SNY, which is sync, dot sequence number. That's not a Q. Oh, is it sequence number? Yeah, it is sequenum. Sequenum. And it sets this equal to X to begin. Now, this is that thing where you change stuff up with the sequence num and the ACK in order to prevent a type of cyber attack that he also mentioned. I forget it by name specifically, but that's the purpose of this algebra that happens. So now you send back the SNY, the sync packet, with the sequence number now equal to Y. And you have an ACK dot sequence number. I'll just do a hashtag for now. Equal to the original sequence number incremented by 1. The original one that was received, X. And then finally, there's the last stage where you receive just an ACK to respond to the sync packet sequence number that was sent here. And this one, obviously similar to you receive this one, you send it back, your number incremented by 1. This one is equal to Y plus 1. And that's the full stage. So you send 2 messages from the sender and 1 message with the receiver. The receiver's message is a compound message, having both the ACK to the originally sent synchronization packet, along with a new synchronization packet with a new sequence number. And then you just send 1 ACK back. So that's the whole process. If you want a significantly more understandable drawing, I recommend jumping over to the, and on your own time, hopping over to the solutions for this exam so you can see it more clearly. And now, what's the difference between flow control and congestion control? So this is just vocab. So I'm not going to write it. I'm going to say it out loud. So the difference between flow control and congestion control is that flow control is designed to protect the receiver from overflow issues. So if specifically the receiver's buffer from being overflowed. And then congestion control has nothing to do with the receiver. It has everything to do with preventing the network that the devices are on from having buffer overflow, specifically network routers. And that's literally the difference. That's how he says it in his answer. That's all you really need to know there. So that's a quick one. Then we drop down to D. What's the potential problem using distance vectored based routing algorithm? List a couple of solutions to addressing this problem. So I vaguely remember this. And I know that there's the count to infinity problem.
Yeah, that's the main problem he's looking for, is that one.
Yeah, because that one's kind of an L. So in count to infinity, distance vector, that's the one where you have, the lines with a number given to them, right? And then you kind of like do some operations across from one node to another and you find the best number. But you can get into loops in that results in this problem where you just have a problem there. So the two proposed solutions are, in my opinion, the one that makes more sense is set an upper limit. So setting an upper limit prevents you from counting to infinity because once you reach a certain length, you just say, all right, we're going to count that as a garbage. We're not sending shit that way, and just take that out of the running as an option to send your data. And then the other one is the so-called split horizon solution. Do you remember what that one is?
No, I just remember that. That's one of the answers here.
I know, I'm gonna look it up real quick. Let's see what split horizon is for. Yeah, it's another thing for preventing loops. So split horizon is a method used by distance vector protocols to prevent network routing loops. The basic principle is simple. Never send routing information back in the direction from which it was received. Okay. So that just prevents, let's say we had 3 nodes. Right? This node sends something here. This node sends something here. Split horizon makes it illegal for this transmission to occur. So if you use this method, you don't need to set an upper limit because count to infinity won't just keep incrementing going in loops like this. It just won't be able to do that loop. So both an upper limit and split horizon work. But now that I know split horizon's main function, split horizon is probably more efficient because you don't need to do a bunch of loops before you terminate that as an option. You can just prevent it altogether from being a problem. So that's nice. Nothing too tricky with that. So far, so good with just a bunch of little vocab things. Now we have a beefier question, but still not that tricky as far as I'm concerned. I have to actually read the question first. A router has the following CIDR entries in its routing table. So you have the address, mask next hop, and then you have that IP, interface 0, another IP at interface 1, another IP at router 1, and then a default router 2. So basically, this is going to be a thing of figuring out these IPs if they fall within the range here and what happens. So first IP. So far 135, it could be either interface 0 or 1. 46, we're still either 1 or 0. 63, okay. 63, 56 is too low. 60. So 63 is going to have to be this one because the way this notation works is it starts with the lowest common lowest common bits, and then these denote increments beyond that. Which means that yeah, I here has to be or 1 in Roman numerals has to be in I1. That's where that should go because that falls into interface 1's IP range. Next one, we see 57. Okay, 56, well, easy. That means it falls into I0's range. Easy. Then we have this one, 52. Well, we have a problem. 52 is smaller than both interface 1's address range and interface 2's address range. And it's definitely not this, it's not router 1, which means this one is going to have to go to your default router, which is router 2. So we'll just denote that R2 for now. Next IP, 192. All right, so far we're thinking router 1. 53, same, so okay, looking good. 40, all right, and then 0, but there's 23, so boom, 7. Yep, this goes to R1 because it falls within R1's address range. Nice. And then the last one, 192, 53, so far so good. 56, we have a problem. 4 is not all zeros, which means 4 is not 0, it's 4, which means that's part of the commonality range of this range of addresses, which means this is out of range. Therefore, yet again, we send it off to our default being R2. And I can tell you that that is in fact the correct answer. And that's how you arrive at it. Easy peasy. Time to scroll down to I think this is the last, no, not, well, it is the last problem, but the last real one at least. All right. So now we have the big problem of the exam, or at least this one. Perform the link state routing algorithm, aka name I'm not going to try to pronounce here. Dijkstra's. I don't know the proper, because the DIJ hits different.
I think it's like Driskras or something.
It's some wacky. That looks Nordic to me. Who knows? For node F, the cost metric here represents latency, implying that you can simply add cost across links. Simple. So here's a good thing to note. We did go over in notes that the cost metric is very important because cost metric dictates how you're able to accumulate. So in this case, latency is a simple scalar time unit. So latency is additive, but there are things that are multiplicative, so you got to make sure you know what. So although it looks like he simply tells you, regardless of what it is, he'll tell you what it's how you're allowed to accrue it, whether it's multiplicative, additive, something like that. And then it says the link state packets sent by the nodes in the network are shown below. When finished, provide the routing table for node F. Link state packets are in the form of destination, cost, next hop. All right. So we have this network here in the form of a graph, no pictures for this one. So starting at node F, all the way over here, we have exclusively tentative ones. So all our tentative ones for node F are denoted in node F's original range. So we can go through here and immediately, basically you take these and you copy them down here in the form of parentheses like this. You'd have A, 10, A, right? And that's it. And then you'd have the other ones following it. And that's all you write there. You write all of them down, done for the first step. Next step though, you need to add one to the confirmed side. So in reality, if you do get this, I recommend like drawing a dotted line down the middle to dictate that these ones are in the confirmed side and these ones are in tentative. So now we're down in the second level. So you have to figure out, well, which one of these three will be confirmed first? Well, latency being the metric here means boom, the shortest path, that being E, node E will be confirmed first because it's faster to just reach there. It only takes 4 latency units, whatever we're looking at here, versus 10 and 12. So we add E4 here, E4E to this side. And on this side, we can now add in, I believe is it node E's access? Yes, it's node E's access. So now that we've confirmed node E, we still have, this one carries down because we haven't confirmed it yet, along with the D12 one, that's still here. This in node E, now we got to look to node E's table since it's been confirmed. Obviously, we're not going to say F since we are F right now. We don't care about ourselves, but we do care about the other ones. So we'll now add B2B and C4C onto the tentative row as well. Now I move on to the next one. So looking at this, so this carries down again, and we have to figure out, all right, which one of these has the shortest path at the moment? Well, looking at it. Oh yeah, by the way, I did make a mistake there. I didn't mention something. So whenever you jump, like whenever you confirm, like in this case, whenever you confirm a node being node E here, whenever you have to write down these next ones here, in this case, you take the latency from node E and you add it to the latency of the nodes you're adding to the tentative. So in this case, it would be B6B and C8C or C8E. Oh yeah, that's another thing. Sorry about that. These nodes in node E, if they're added from a node, the last one being its next hop, your next hop gets replaced with the node that you just found those nodes from, which is E in here. So that's what you end up putting. So that's just that. Next thing we do is we look through the list of the nodes in this tentative row and we find, all right, what's the shortest one here? Well, we have a 10, a 12, an 8, and a 6. So the shortest one is B6E. So now we confirm B6E on this row and so on and so forth. So that's exactly the process. Those are the simple rules for how you do this. There is a solution you can fully trace through now if you want to figure out where everything came from. But this does take a bit. My handwriting's garbage with a mouse. So it wouldn't really be helpful too much anyways. I've explained the main principles being from your starting node, your first line is nothing more than copying what's in your starting nodes column and rewriting it in little parenthesis bubbles. So it'd be A10A, D12D, and D4E. Your next one is find the shortest parameter out of those ones that you copy down and bring it over here to the confirmed row. And then from there, you confirm and modify the confirmed nodes entries that are still viable, add them to your tentative row, and move on. And you do that process over and over again until you've filled everything. At the end, from node F, everything that node F is connected through should be in the confirmed row, and there should be nothing left in tentative once you're done. So that's a good way to check yourself. But then at the end of that, you create a routing table. Oh, we don't want that. Create a routing table. So when you create a routing table, you go to your final, at the end, you'll have a confirmed row. And in there, all you have to do is look around. So in the final confirmed row on his solutions, E's cost is 4, D's cost is 11, C's cost is 12 or 7, B's cost is 6, and A's cost is 8. And then your next top is what you list here. So in this case, next top here ends up being E for all of them. Yeah, ends up being E for all of them. And let's look here, see why that is. So originally A10A in the second row. And then here, once you've confirmed B is the next one. From B, yeah, you update and overwrite nodes once you find shorter paths. So that's fine. That follows with the principle though. All right, so that's that exam. Now there is one last question. Which of the following characters is not a superhero in Marvel? So first things first, Spider-Man is a superhero. Iron Man is as well. Now you might think X-Men is a miswrite of X-Men or Professor X or something, but that's wrong. X-Men is in fact a Marvel mutant. He's a very obscure one, but he is existent. So the last thing we have here were two options, none of the above or Ip Man. So Ip Man is a series of very popular martial arts films. So this is not in the Marvel universe. So none of the above is wrong. Therefore, Ip Man is the winner. Very important information here. There's that. So now let's go to the mouse here, pull up this one, see if there's any real differences. See, you are designing a reliable byte stream transport layer protocol to operate over a 10 megabit per second network, or 1 times 10 to the 7th bits per second network, whatever you prefer, and is using a sliding window for flow control. The time for keeping the transmission pipe full is taken to be the RTT of the network, which is 50 milliseconds. Each number in the advertised window or sequence number represents 2 bytes of data. Okay. What is the minimum number of bits necessary for the advertised window field of your protocol header? So this is a flashback to homework 4. This is a question that was asked in homework 4. Provide this minimum number as a whole number. So yeah, okay, fine. Let's see. So first thing first, we need to calculate how many bits need to exist to keep the pipe full. So as I mentioned earlier, keeping your unit straight works. What's the information we have available to us? We have the bandwidth of the network and we have the RTT. Since that's the only stuff we really have that's useful here, bandwidth is in bits per second, RTT is in seconds, and we want data here to begin. So if we do RTT times BPS, that's bytes, but BPS, right? So 1 times 10 to the 7th times 50 milliseconds will produce 5 times 10 to the 5th bits of data here. But it's rather important that we keep into consideration each number in the advertised window or sequence represents 2 bytes of data. So what we need to do is we need to take this. All right, what is it? What is it? So there's this to start. And then we do 2 times 8 to fulfill this requirement. times 2n is greater than and equal to 5 times 10 to the 5th power. So basically we're solving for n here. So it just has to be greater than or equal to. So once you go through the calculus for this, or not calculus, once you go through the algebra for this, you'll come to having n needing to be equal to 18 for this to be satisfied. So pretty simple, nothing too crazy. Part B, how would you choose the sequence number size in accordance with the advertised window as determined in A? So your sequence number needs to be greater than or equal to 2 times the advertised window. Therefore, you're looking at 16 bits. Did we even determine? Yeah, we did determine our advertised window size. What is the minimum number of bits necessary for advertised window field? Provide this minimum as a whole number. So we said 18 here. That's what he says. Yeah, 18. So how would you choose the sequence number size in accordance with advertised window? So it has to be greater or equal to 2 times. Do you see a problem here? I feel like there's a problem here. It says greater than or equal to, and yet it's 16 bits.
I think for A, I think he put, I think it was supposed to be 15 because when I solved that, I got 15.
Then it's, yeah, okay, then his handwriting is just stinky. So n's equal to 15. So, but then 2 times 15 is 30.
Well, it's,
Oh,
yeah,
you're no, yeah, no, you're right. It would just up it. That would just bring it up to 16 bits because it's binary. Yeah, okay, I see it now. All right, so that means since the rule is greater than or equal to, you can make it equal to. Yep, all right, I see it. Yep, 16 bits, 16 bits, that's the answer. Bonk, bonk. Got some quick fire short answer questions. What is the difference between flow control and congestion control? I already answered that. What does the BGP gate or border gateway protocol only find? Why does the BGP border gateway protocol only find a possible but not optimal path to the destination or autonomous system? I think the shtick here should be that autonomous systems, those being the big shadow entities that are somewhat responsible for the internet at large, there's like 50K of them globally, I think. These ones are all kind of, as mentioned, they're autonomous. So whomever the admin is for a given autonomous system is allowed to choose whatever parameter they want to define optimal, whether it be latency, whether it be, reliability, stuff like that. So in that case, it means the reason it's impossible but not optimal is because different autonomous systems have different metrics, which makes it impossible to find a guarantee solution, just a good enough solution. Because there's too many switches between parameters for you to find a true answer. Draw the three-way handshake and we did that already. What makes the estimation of RTT and TCP difficult? So the answer here should be that it is a connectionless network. So, or TCP is a connectionless protocol. So not only is TCP not aware of the connection path that it takes to its destination, but its destination path can also change wildly between transmission of packets, which is why we have to use iteratively updating estimations to figure out what the RTT is, and we can't just assume a stagnant one. So his specific answer that he said is as simple: there are too many intermediate devices for end-to-end connection, but any type of answer resembling what I said or he said would be acceptable. So if you want to connect 1,200 devices with the internet and you're only allowed to get one IP class block, which IP class will you get for the highest IP usage efficiency? What is the IP usage efficiency in this situation? And then he gives you the formats of A through C IP addresses. So let's see. Bonk. So he goes in here and he says, so if I'm not mistaken here, a class A is the broader one. And as you go down, you can represent less and less IPs with that
Yeah.
because your host is the
Mhm.
one you're interested in. So since the host block is what you're interested in across these, you go through and you think to yourself, all right, well, starting here, 2 to the 24th, and it was 1200, is many times greater than 1200. So class A, too broad, not worth it. Now here, 2 to the 16th is still greater than 1200. So it might not be the answer here, but I think we all know that 2 to the 8th power is smaller than 1200. So we have no choice but to select a class B address. So your first thing when you say up, we pick class B. And then your next thing is efficiency, but efficiency is a simple thing of what you need over what you get. 216. So when you work this out, you get a pitiful efficiency of 1.83%. That's good stuff. Well, not really. It's bad stuff, but it is what it is. So that's that. So we will clear those doodles and move on. A TCP packet has been encapsulated in an IP packet. Answer the questions about the following IP packet. Values shown are hex. So each individual character represents 4 bits, yada, 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 extra information. First one, what is the total length of this IP packet? Give your answer in the total number of bytes. Are we just, I mean, it says it's it's in the length header. But I guess somewhere he gave us,
He gives the chart, I think, on like the next page.
yeah, that's exactly what you need. You need the chart. So let's look at the chart. Where's that gonna be? I need to zoom in on this. Let's bump, bump, bump. Yeah, all right, better. So the first thing is find the length field. So let's look down here. Length. So starting from 0, which would be, you know, oh my God, no, I went too far. Starting from 0, which would be up here. We go over 16 bits, which means our length and our length field is 16 bits long itself. Yeah. All right. So what do? We look up here. Well, he said each character is 4. So here's your first 16 bits. So here's your length field. So you do 47 in hex, convert it to decimal. So let me go back to that hex to decimal converter. So you'll just do this in your head with a calculator or something. I'm going to do this on my computer. So we have 47 and we get the decimal number 71, which I know is the correct answer. So for this one, you just count over till you find this field and you find that it's 47, convert that. No, you have 71 as your answer. 71 bytes. Remember the unit, bytes. TCP is a byte oriented protocol. 71 bytes, right? B, given the above finding, what is the percentage efficiency or meaningful data in the IP packet? And then he gives you a fat hint here. It is the ratio between data payload size and the overall IP packet size. IP and TCP headers are not meaningful data. All right, well, let's go down here. All right, so let's see how much data is useless. Yeah. This is so bad. Where's the IP? So this is the IP header for the length of the message, but
Yeah, I
ugh,
was confused on this one.
that's so annoying. All right, I'll figure it out in a second. But the first question was, what's the length of the IP packet? So you get that right. That is still the correct answer using the IP header information here. All right. All right. So here's what you do. Here's how this works. So Let's draw a picture. Let's draw a picture of the shitty OSI model, right? So here's your stack, right? And there's your layers. So we're at TCP, so we're over here, layer 4 or whatever, and IP is a layer 3. So boom. So as you know, this is my computer, right? I'm over here. I'm like playing Minecraft or something, and then I send it down. So I'm at TCP. So I produce this TCP header. So here's my TCP header, but then it goes down another level. So here's my TCP layer, the core of the onion, but then it goes down another level and it gets encapsulated by IP header, the next layer of my onion, right? So what ends up happening here is the TCP data and header are all included in the data field of the IP header, which means we have a way out. We have an answer here. So let's go up. Well, I've got to count first. All right. How many rows we're looking at? 1, 2, 3, 4, 5, 6 rows. So 6 times 32 is the amount of bits. And we got to divide that. So let me get up a calculator since I'm slow. Calculator, online calculator. So we have 6 times 32. I said 32, not 31. 6 times, oh my God. 6 times 32 is equal to 192. We divide this by 8. That's equal to 24. So remember, we know that the total length of this entire system is 71. So far, we just lost 24 of our 71 bytes to IP header. All right, good. Now I move on to the next section. 1, 2, 3, 4, 5, 6. Well, same unit. So what does that mean? It means that the TCP header also consumes another 24 bytes, yielding 48 bytes of waste, completely stinky, useless information. Now what do? We do 71 minus 48. Yes. And that's useful information over total utilization. And now we have an efficiency of 32.4%. Complete and utter garbage. Do you get it more now? Do you understand it?
Yeah.
Yeah, it's the onion. You got to remember the onion, you know. Ogres are like onions. They have a lot of layers. It's important. All right, moving on. What is the destination IP address? Okay, well, let's go. Find destination in here. Destination is the 4th row, 32 bits long. So 32 bits is going to be 32 bits is, then it's 4 rows down. So 444. So it takes 8 hexadecimal numbers to represent 32 bits. So we go back up here. That was 4 layers down. So we have 4 layers of 32. So nope, nope, nope. Let me scroll down again. It's the, yes. Oh wait, what was asking? Was asking the destination? Yeah, it says destination. All right, so we cut. All right, so we've cut 3 out so far. Dead, 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 dead. So this is your IP. I really don't want to convert that right now. But we have to. All right. So 9 to a 5 6 4 3 F. That's what we're looking at here. That's what we think the IP is. We got to put it into this form. So it's octets. So we got to take this, right? We got to turn it into a binary stream. Cut it into octets. Oh wait, no, we don't. No, here's the answer to that. We don't need to cut it into binary stream. Separate it into bricks of 2. So those are your 4 fields of IP. Convert these to decimal. So let me do that. So starting with 92, we get 146. So we have 146 dot Then we go over here, we go to A5. And then we get 165. Next one is 64, which is cool 100. Last one is 3F, yielding us 0. Well, yeah, it's 6.3. You don't need to write it like a populating the field. And the actual answer in these solutions is just that. So that is how you find the IP. It's just a matter of understanding. I mean, it's not even really a matter of understanding, honestly. It's just you open your eyes and you look at this and you'll be fine. And the next one, last one for this section, is what is the destination port number? Yet again, destination port number, which is in TCP. Yep, TCP. Oh no. Okay. I'm gonna do this just because I'm nice, but I really don't want to because I'm lazy. As mentioned previously, onions, right? Good food. But another thing that's important here is that the TCP header in its entirety, along with TCP's data, is encapsulated in the data field of IP. So in order to even begin figuring out what's what, you got to count down 1, 2, 3, 4, 5, 6 levels of 32 in this data. So that means we do 1, 2, 3, 4, 5, 6. All right, we've done that. We've reached the TCP header. And now we go to the TCP header and we've realized that it should be, so we cut out just this, and this should be our TCP header. Oh, sorry, this should be our destination port number. So this should be a single, so this is A0F4, 4. Yeah, that's good enough for me. All right. And that's what we're looking for. So we'll go back and I'll use my hex converter to, I haven't all that. Nope. All right. Hex converter, please. Thank you. And I take this and I turn it into a decimal number. So we're looking at A0F4. And the answer we received on the converter is 41204. So let's check. That is the answer that he got too. So that is correct. So that's the mechanics of counting down and finding data in the headers, given a string of data. So there's that. Continue on. Router has the following entries. We did this already. We did this on the last one. Interface 0, 1, router 2 thing. We already did this. Well, wait, let's see. Right the next hop the router selects when it receives IP packet. No. We did this. Yep, we did this already. We don't need to do it again. Link state routing. We did this too. Yep. Don't need to go over that again. All right. This is learning bridge stuff. So I might not even remember how to do this myself. Let's see. Consider the following network where W, X, Y, and Z are nodes. And B1 and B2 and B3 are learning bridges. Designed from homework 3, question 2. Cool. Don't know if that still holds in real life. Assume that the forwarding table for the 3 bridges are all empty when 3 transmissions are made in the order shown. Okay. In the above networks, B1 has interfaces. Okay, well, that's unnecessary to see. So we have X transmits to W. I gotta scroll down here so I can see what's going on. There we go. Bonk. Right here. So it said X transmits to W. So we go through here. So what has been discovered with an X transmission to W? So when X transmits to W, it goes through 0. So that's the interface. And its destination was W. Okay, so its interface goes here, and that's B1. So B1, its interface with X is 0. And then the next one, B2, its interface with X is 0. And then we go to B3, its interface with X is 0. And then we go to W. So for B3, sending to it, it doesn't know it yet. No, what the heck? All right, so far we filled up, clear this, log. So with a transmission of X to W, we've successfully deciphered that the interface for X across the board is just zeros for all the bridges. So then the next transmission. Is there ever a W? Yeah, here's since there's never a transmit. So here's the shtick with the learning bridges, right? So when I said X transmits to W, right? The bridges have interfaces with what they're passing data through. They don't record an outgoing interface. So when X goes through, B1 says, hey, X connected to 0. I just got information from X. B2 gets information from B1, but B1 tells it got it from X. So B2 is like, oh, hey, I just got information from X on my interface 0. And then B3, so on and so forth, interface 0, X, boom. All right. That allowed us to fill out the first row, or the row for X, with 0, 0, 0 in your interface. But remember, the learning bridges can only operate on inputs. They cannot record where stuff goes on the output, which means for W, there's never a message where W transmits to anybody else, which means W's interface to the rest of the world is unknown all the way through, since there was never a transmission from W to the rest of the network. It only received data. It did not send any itself. So that's your first 2 rows done. Now let's go to look at Y or Z. Z transmits to X. All right, let's look at that path. All right, this path is equally simple. Bonk, like that. All right, well, that means B3 is going to say, so Z's entry for B3 is going to be, hey, I saw it coming on 1. And B2 is going to say, hey, I saw Z coming on 1. And then B1's going to be like, hey, I saw Z coming on 1. And then you say, boom, I've reached X. So if we clear all the drawings and scroll down, Z would have 1, 1, 1. And I can confirm that the answer says Z is 1, 1, 1. That's what fills it. So our last thing is Y's interfaces. So let's scroll up. Y transmits to X. Let's see what happens. Oh, okay. It only goes through 2 interfaces, but Y transmits into B2 through that 2. So it says, hey, I saw data come from Y on 2. I know where Y is now. And then B2 sends it in on 1 and boom. But you see B3 never got any input on any of its interfaces from Y, which means your final answer, your final column, or your final row, I should say, in here for Y will look like a B1, it came in on a 1, B2 came in on a 2, and this is yet again unknown since no inputs came in. So that's that. So that's the explanation for how to do the learning bridges. So that's cool. Bonus, what do you expect? What do you expect the course to change to keep or to keep in the remaining semester? I think we can all agree we want more quantum networking. Because why not? Everybody loves matrices and probability. Oh, that's all that. All right, those are the 2 exams. And the solutions are online to check over stuff and try and look over it more to figure it out. But that's that for this one. You got any questions or concerns or recommendations for the body politic?
Overall, the hardest thing seems IP packets, IP, like figuring that out,
Yeah,
because it's
figuring
binary
out
and
like
text and-
figuring out data from like this thing.
Yeah,
Yeah, this is a tricky one, but it's not that bad when you realize when you're given your headers. That's why for a moment I was confused. I'm like, well, what the hell are we gonna do if we don't have the the header chart? But yeah, now we're good there, so that's chilling. But yeah, I don't think this exam will be that tricky. I went in like with nothing more than last time's study session in terms of review for the last exam. And I made one mistake that resulted in me not getting an 100, but if I hadn't made the mistake, I would have gotten an 100. Instead, I got an 84 because I'm pathetic, but it'd be like that sometimes. So similar with this one, I don't actually think his exams or tests are unfair or difficult. It's really
No,
just a matter of
knowing the material.
just working them out. I don't think they're
Mhm.
bad, so. I don't think
Yeah.
anyone else really thinks they're bad either. The average is
No.
fine. I think it was like a 60 something.
It was a 70 something, I
Oh,
think.
yeah, okay, yeah, that's even better. Yeah, so that's just good. You got any comments for the body politic, Brett, before I close this up?
Not particularly. You think it'll be more like this and less like the homework? Because the homework was kind of weird.
Which homework?
Like homework 4 was a little, like the last two questions were a little funky.
Most of homework 4 has stuff that's outside of the range of what's on this exam.
Yeah,
Like
that's what I thought.
those
but
last two questions specifically are like chapter 5.3, whatever stuff that's out of range, because 5.1 is the highest chapter we'll be covering for this exam. So we won't see any iteratively updated RTT, like any of that. We won't see anything like that.
Yeah, and those seemed a little long for.
They're long for a test too. They'd be a little, and making you do it by hand calculations when on the homework, he explicitly says, like, use Excel or something, because it's
I
horrible
did it
otherwise.
on the homework.
You did it by hand?
Yeah,
Bad decisions. I
Oh,
see.
no.
yeah.
Dude, some of them went up to like 20 iterations.
It went up. I think it went like to 23.
It grinds. It'd be like that. Yeah, but that's that. So I'll post this. Everybody have good luck on your exam. Simply get an A. Probably not. I promise it's probably not that hard. All right. It's bedtime. Adios, gamers.
See ya.
See you.